Good. Okay, we've got two interesting talks to finish off with, and the first one is from Chris Densham, who is going to tell you all about engineering high-powered targets. So over to you, Chris.
Okay, right. Thank you. So you heard a lot this morning about particle accelerators and how to make them. So I'm going to balance that by talking a bit about particle decelerators, or otherwise known as targets. So they're very simple things in principle, unlike particle accelerators, which are clearly highly complex pieces of kit which accelerate particles over lots of clever kit, lots of power to generate a high energy beam or high current beam, and then you try and stop it in like a foot or something like that of material. And so this is to generate, typically you put usually protons, which is what we've heard about this morning, into usually solid metals, tungsten or graphite, both refractory materials. Higher powers, people going to have used contained liquid metals, or liquid metal jets have been proposed, and in some cases used, and also powder materials maybe. To generate neutrons, which we've heard about this morning, also facilities that generate neutrinos from pion decay. Also other things to make radioactive isotopes and positons and p-bars. So we kind of most people work in these individual areas, neutron facilities or neutrino facilities, but we kind of we have a group here that kind of focuses on targets because, well, one thing it's kind of seen in many cases as a kind of an Achilles heel technology. Some people say they always go wrong, which well, maybe they often do. And there are synergies between lots of different facilities and applications. Or when that's being fancies, and when I say synergies, what I mean is same things go wrong in different areas. So the idea is to maximise physics output by optimising the engineering. So to start with, locally, ISIS, the first target station, has been running very well for 30 years. Now, the first target station hasn't seen a significant upgrade in that time. So the thought is that maybe it's possible to actually use some modern techniques to actually improve the performance. Not that it's behaved badly, but one could do better with the same beam power, perhaps. So this is the model. The target sits on the end here, it's a tiny thing here, and then you've got all of this infrastructure behind it, big shield plug and all the cooling plant behind it, trundles it in and out of the target station. So here's the first target here. It's a big hunk of metal, tungsten plates cooled with heavy water. It's quite a big beast. And the idea is to try and make this a bit more compact. You need a material to make neutrons, but you don't want to have extra material to then absorb them. So the idea is this is kind of where we're at now, which is like much smaller than this. It's kind of a water-cooled plates still, but much more streamlined. So this is the current ISIS-1 target. These big water channels here, heavy water, and lots of stainless steel, absorbing neutrons after they've been produced and causing backgrounds and moderating the neutrons when you didn't want to. Now this is the objective of what we'd like to go more towards. This is the second target station, which has got a good neutonic performance, but that takes 1 pulse in 5 from ISIS, runs at 32 kilowatts, but very good performance for 32 kilowatts. And the TS1 runs at now on 200 kilowatts. You can see this is where we're at the moment. It's not a completed project, but the idea is it's somewhere trying to get it towards this sort of size, but certainly it's a lot more compact than the existing one, albeit with it's got the same actual amount of material that interacts with the beam. So where we are at the moment, there's much less. This is where it's kind of not finished yet, but this is where the current design is. Big reduction in amount of stainless steel, so that's good because that's one of the big problems of activation when you throw these things away. Much less tantalum. That's also good because tantalum is a big source of decay heat. and about the same amount of tungsten. And also less heavy water, so that's less absorption of neutrons, moderating neutrons when you didn't want to. And that's achieved by just nothing revolutionary. ISIS doesn't want anything revolutionary. Reliability is the most important thing. So this is the existing plates. These are the temperatures, and you can see the maximum temperatures near the front of the target. And by juggling with the size of the plates, it's been possible to get. I mean, it's got 12 plates. This now has been reduced down to 8 plates, and the temperature is now sort of uniform, the maximum all through those plates. So that's the sort of way that's been done, and the stress is all about the same. So it's should be better performance. Although the main thing comes down to the moderators. This is just to get the target material out of the way. So that's ISIS. Now going on to you heard this morning from Dave about the ESS. We did do a study for the ESS a few years ago on the target wheel. So they'd already settled with the idea of a big rotating tungsten wheel to distribute the beam power, and we came up with this sort of idea. We want to pack as much material as possible. So we thought, well, we use the inspiration of a sunflower seed head to try and pack as much material in. That is kind of nature's solution to closely packing material. And the idea is that we'd have helium flowing between the seeds, and it would find its way through. And so this was kind of what we proposed, approximation to that. Helium flows, between all of the seeds here. Beam goes in the front, and then so we thought it's very similar to having a whole load of ISIS targets just bolted around on a big wheel. This was our suggestion. So the helium flows in around the outside and then through all of the plates here. And this is the flow pattern. So it's a bit like a heat exchanger, really. So this is what we kind of suggested at the end of our study for the ESS, and Bilbao are now taking this forward. And I think they're taking elements of this proposal forward, and I guess they must be making it by now. Okay, another tungsten target wheel. This one doesn't rotate. It looks like a bicycle wheel, but it actually stays still. Much lower power. This is for Fermilab. It's a muon production target. This is a tungsten. It's just the size of a pencil, and it's 8 kilowatt beam goes into that. And so we thought, for simplicity, that just radiates its heat away. So it just sits inside a solenoid to capture the pions as they're generated. And we have all these sort of tungsten spokes here that hold it in position. And it's got the beam structure is a bit strange. So it's 15 hertz for a bit, but it's got a 28% duty factor. So this is the sort of you can guess the beam structure from the stress distribution. So you get a load of bunches here, like small gap, and then some more bunches there, and then a bigger gap, and it all cools down, and the stresses go down, and then just over a second later, you get the same again. So you get this rather awkward stress cycle, which we were a bit worried about with this pencil of tungsten glowing like a light bulb. And Peter Luffridge came up with this rather nice idea of putting a pulse beam through a sample. So this is a tungsten rod here that's been EDM machined in the PDF lab here. Did a very nice job. And so the current passes through this. It's a pulse current, and you generate a sort of thermal stress in this little bit in the middle here. And this shows the stresses here. So you kind of see it's a much higher rate. And you choose a temperature by increasing the rep rate. So that gets us to the same sort of temperature. You can see it glowing here as the real thing. So we're testing the temperature and the temperature jump and the stress wave. Sorry, not the stress wave, the stress oscillations the transient stresses. So it's testing everything in beam. You can see it looks pretty, it's quite similar. It's as close to that as we could realistically get. And after 10 to the 8 pulses, it eventually, well, it was actually doing well after 10 to the 8 pulses operating. So we turned up the wick a bit, and then it did eventually fail. So it looks quite feasible. It doesn't. We've tested everything we could except for the radiation damage, which is a lot. So it's still unknown. So now for something completely different, and on the other side of the planet, this is a plan of the T2K facility in Japan, right next to the Pacific. Remarkably close to the Pacific. It got a big hit from the Japanese earthquake a few years ago. It got a magnitude 8 sort of earthquake here. So it's only one down from the magnitude 9, just a little way over that in this direction. And the LINAC by the end of the earthquake wasn't quite as linear as it was supposed to be, but it was managed to sort it out in a year. Sort of tweaked the magnets and stuff and got the beam going through it, and it's up and running now and working very well. The 30 GeV beam from the proton synchrotron is bent around on the inside. It's extracted on the inside of the ring. And then it's focused into this target station here. Generates beam of neutrinos as pions decay here, and the beam dump is here. And the super K neutrino detector is 300 kilometers away. And so this is a side view of the target station. Target station here. This is a decay pipe where the pions decay to produce neutrinos, and then they go into the remnant beam, and the muons go through this beam dump here, which is a big room of graphite, and that's me standing in front of it before the beam got switched on, I hasten to add. So that's a view of the target station. Target sits in a magnetic horn here, and then there's a second horn and a third horn, and these are pulsed, special pulse magnets which focus the beam in the forward direction. So here's the whole magnetic horn assembly sitting at the bottom here with the target stuffed in it. So there's another view you can see of that. It's a very simple thing. It's just a graphite rod. That's it, just about a yard long. It's as simple as that. And the proton beam comes through, interacts with the graphite rod, produces pions, and at the same time, this horn it's like a trombone, is pulsed with like 300 kiloamps. And that generates a nice magnetic field, which focuses the pions in the forward direction so they can decay. Now, the target design we came up with, you have helium, it flows in a beam window here, and then it sort of flows on the outside of the tube. And you can see this is a CFD simulation that Mike Fitton's been doing. And he's actually been doing this for an upgrade. We're now about to upgrade it to 1.3 megawatts. So you can see it cools the window here, helium flows along there, and then back again, and then it goes out here. So the idea is you've got to get good helium cooling, but minimize the pressure drops in and out. Now, radiation damage of the graphite is a big concern. I mean, there's various facilities that run with graphite. It's a good refractory material, but it is susceptible to various things like swelling and loss of thermal conductivity. So this is a graphite target that's run at PSI. And we haven't had as many protons, haven't had as big affluence as this, 10 to the 22 protons per centimetre squared, but we're headed in that direction. So one thing you see in this plot here is the drop in thermal conductivity. I mean, graphite to start with it starts at 1, and then a little bit of radiation damage, so we're certainly on T2K. We've had this amount of damage we're down to here somewhere. You can see the thermal conductivity plummets to like about 25% of what it was. As if you let it run hotter, it's better, and cooler, it's worse. So we run it hot. That's why we cool it with graphite. So we're on this kind of curve, and this simulation assumes damaged graphite. But that has worked. That's worked very well so far. I mean, it is a simple graphite rod, but you've got helium flowing past it, as you can see here, like 400 meters a second. So you imagine if you had if your target was looking anything like this, you'd have little bits of graphite falling off. So it's all working well so far. One of the other things we worry about is the bunch structure from the beam generating stress waves in the beam window. I mean, the helium is held in by a thin beam window, and you have this bunch structure here. We have 8 bunches per spill in a 5 microsecond spill. Now, it turns out that if you have a 0.3 millimeter thick window, then the stress wave can oscillate and constructively interfere. So each of these 8 bunches are coming in here. You get 1, 2, 3, 4, 5, 6, 7, 8 bunches, and these interfere and generate quite a significant stress by the end. But if you make it thicker, 0.5 millimeters, then the stress waves destructively interfere, and who we see along here. So you can see that 0.3 millimeters is bad. 0.3 and a bit is good. 0.5 is better because it's a bit more tolerant. So Andrew Atherton has been doing this just now. Don't ask what the thickness of the actual window is that's running at the moment. So we obviously expect these targets to fail. So rather than throwing that entire horn system away every time just a yard of graphite fails, we came up with this remote handling system. Same sort of idea as ISIS has here. Manipulators you look through a lead glass window to pull targets out and put a new one in. That's the idea. If this one fails, you pull that out, slide a new one in, helium pipes here, helium pipes plug into there. Targets haven't failed yet, but last year one of these ceramic brakes failed. It was actually because this helium pipe expanded with the heat and stress relieved a bit, which is kind of annoying. And that's what we think's happened. Anyway, this ceramic brake failed. So we hadn't expected to have to do this. We did manage to change. You can change the helium pipe. So you can see this new one doesn't quite match the old one. We kind of guessed that was a problem. So we were making this replacement pipe. And then when we discovered that actually was a problem, we were ready to fix it for over Christmas last year. So this is the one that's now running, and it's working fine at the moment. Okay, I just showed this picture because this is a target which we made for another one for Fermilab. This is a NOVA target, which is a similar sort of thing, but because we're trying to capture a different energy of neutrinos, it's actually upstream of the horn. And anyway, this has just been pulled out. I heard this week that this has finally failed after a few years of running. This bit didn't fail that we made. It was the beryllium windows that Fermilab made that failed. But there you go. It had to die at some point. Okay, I'll rattle through. I see I'm getting on. So a future proposal which we're hoping to work on, if STFC manages to find the money to pay us to work on it, is LBNF/Dune. John Wormsley mentioned that this might be getting funded if you listen to the autumn statement from the Chancellor, so I have to be optimistic. So we came up with this as a spherical array target. The idea is that helium swirls in a spiral, multiple helix spiral, and it cools all these separate chunks of material. And here we are testing something similar, a packed bed here. So this is something we'd like to pick up on soon. And here's something else that Tristan did. It's an increasingly granular material. So it's a packed bed. So this plot shows limitations of different types of target materials. This is the deposited power on the bottom here and the temperature jump here. Now at lower powers and temperature jumps, you can get away with just a monolithic target. So as I was talking about, T2K is here. It's just a long single rod, and the ISIS second target is here. then as you increase the power, you have to typically segment the target to divide the heat load and the stresses and so on. And the ISIS second target, ISIS TS1 is here. And what else? Yeah, a few other things. As you get increasing beam powers, then you have to do something a bit more drastic. So you have to either move the target material around to spread the damage and heat load around. So ESS is here, so that's a rotating target. And way out here is some crazy thing for a neutrino factory. So that's kind of way out there. Now, ESS have found that you can, a good solution is to have a big wheel. It spreads the heat around. But ultimately, targets do get a hard life. These are some sort of horror shows of targets that have died over the years. So you can design them nicely, but then nasty things happen to them in reality. So we thought, well, given that they're going to break anyway, why not start with something that's already broken? So we've developed this fluidized tungsten program. I don't know if I can hopefully run these videos. This is we made a jet of tungsten, and here is a contained flow of tungsten powder in a pipe. It's discontinuous, and this one is continuous flow in this tube. And this is we've done this here in at Rutherford Lab using this rig here. We circulate the tungsten powder around you just suck it out and with a vacuum, and then blow it through with air. So that's our proposal. But we thought, well, how does it perform in an actual pulsed proton beam? Because the idea of this was for a neutrino factory. So we did an experiment at CERN's high-rad mat facility a few years ago. In fact, we were the first experiment to ever run on this new facility, so that was great. And we were expecting it to be quite boring, but actually something interesting happened. That's what happens when a pulse beam goes through. We thought, right, that wasn't quite what we were expecting. But it was interesting. So we did another experiment to try and work it out a bit more. And so this last year, we did various experiments in vacuum to start with. It's got the same effect in vacuum, so it wasn't an aerodynamic effect. And then we tried different sizes of particles. So this is fine stuff, and this is coarse stuff. And the beam goes through there, and we've got this interesting lift. So we're trying to work out we've got nice videos of all of this. So we're trying to work out what's happening. It's quite. The idea was to be really simple, but it turns out there's some complex physics in how pulse beams interact with powdered material. But certainly we found there's a acceleration due to the charge. As a proton beam goes through, of course, it charges the material, and that we can see accelerates the lift. So actually, when you plot a grain, it actually doesn't just behave in a ballistic way. It actually they get accelerated up, and they're slowed as they fall down as well. So given that happens in vacuum, we deduce that's a charged effect from the proton beam going through. So we're having fun working out all of that. Okay, so now, but even still, you can't escape material effects, beam windows. Although it's interesting to hear ESS want to get rid of a beam window. You can see why. So when you look at something like this was supposed to clarify radiation damage effects in materials by Colin English. He's from next door at Harwell. To me, that says, okay, we just need to call in the experts here, like Colin. And so we now have this Radiate collaboration, which is a collaboration of willing enthusiasts. The idea being to get these nuclear material scientists and bring them to and their techniques and knowledge to our challenges of targets and beam windows. And this is something from Oxford. They've worked out they can make these focused iron beam cantilevers, and then they put a stylus and push down on there and test its mechanical properties. This is just like a couple of nanometers long. So they're quite remarkable what it's possible to do. So you can deal with very activated materials, but because they're such small quantities, it's not too bad. Okay, so that's it. So that's thanks to all of our collaborators who we've worked with in recent years. Okay, thank you.
Thank you very much, Chris.